all of 6-3 in about 6 minutes, which meant I'm like, hey, what the heck, let's start 6-4, because it's all kind of the same thing as what we've done before. So what I'm looking at doing, and it works out really, really well for our favor, is that instead of just taking 10 minutes to talk about 6.3 and then just working, why not do both of them? It takes 20 minutes. We have 25 minutes to work. And then tomorrow we can answer the more questions, and I got review for all 4 of the sections to quiz them on Friday. I think it worked really well to kind of move things up just a little bit, because it is really fast. What's that? Today's Wednesday. I know, right? The other thing is that when I go back and I looked at how this stuff worked in previous years, obviously it was a different chapter, different textbook and all that. These first 4 sections were done in 2. So they're stretching out the material when it doesn't need to be stretched as much as it seems. So we're using properties and things that we've done. We're just using it a little bit, ever so slightly different within the radicals. So, excuse me, yes sir?
Can I just like move up over there?
Absolutely not.
Oh no.
Of course, man. The look on your face at first, you're like, wait, what? Murphy guy's a jerk. Anyway, you're supposed to say, no, Murphy, you're a nice guy. Thanks a lot, jerks. Shut up, you're being condescending. Anyway, so, hey, guess what this is? This is all it is, guys.
Hey, Mr. Murphy, what do you call Kirby going down the stairs?
I don't know.
A condescending condescending.
It just happens. All right, so guys, all this is combining like terms. You've done this many, many, many different times, whether they're with variables and exponents and polynomials, with imaginary values or whatever. Now we're just working with them with square roots. All the same rules apply. Nothing has changed. For example, can I combine these two? Why? Same thing underneath the radical, same nth term, same radical. So, deep breath, 3 minus 2.
What is 1?
2.
It's 1, so my answer would be the square root of 5x. And again, the reason I can do that is because I have the same nth root and the same jump underneath the radical, which you guys all knew from before. Can I combine this one?
No.
Why? What's different about them?
Every
Yes! The nth root is the same, but the stuff underneath the radical is different. The variables are the same, but the exponents are different. I cannot combine those. Those are not like terms. So my answer is no.
How do you say it in Spanish? No.
Nada.
So in FX, how would you just write the same thing? It doesn't work.
Or you might be able to do that. I don't know.
Sometimes you can do
Or I might just say no solution, or in fully simplified form.
I've never seen that yet. I'll figure it out. What is nothing?
Can I simplify this one?
No.
Why? What is that little guy up there called? The nth root. Yes, sir.
The nth term is different.
The nth term is different. So our answer is no. Yeah.
That's what I figured. My brain's like not good at this.
But
no way this can be jaded.
what can you do here? You can do math. Very good. Yes, you're right. You have to do math. Is it possible to create comparable roots?
Yes.
Yeah. So this is where it gets back to the idea of trying to simplify square roots or simplifying cube roots. More often than not, the simplifying of square roots and cube roots will be values that you're going to be able to figure out without too much of a hassle. For example, the square root of 12. You guys, I really, really hope you know what the square root of 12 is. 4 root 3.
That was a tough one.
It's 2 root 3.
I was almost like, that wasn't right.
Who said that?
Who said 4 root 3?
She meant 4 times 3. The thing is, you just wrote it down. You didn't even
It didn't.
Hey, Josie.
Is it June
It
yet?
was just like,
All right. What is the square root of 75? All right, so this came up a little bit in some of the other ones. Sometimes when you simplify radicals, remember you're looking for the perfect square. There are 3 quarters in 75 cents.
wow.
And then what about the root 3?
It's a 1.
It's a 1, very good. So, what's 2 plus 5 minus 1? What's 5 minus 1 plus 2? What's negative 1 plus 2 plus 5? What's negative 1 plus 5 plus 2? Does it matter which one you do first? So your answer is?
2 plus 5 minus 1. 6. That was a toughie.
What do you think?
Your fingers are sweating.
What's up, Anna? Okay.
Accomplished.
Ooh.
Oh.
Anna! SMRT!
I was gonna tell you, I want to pass this
Anna, what's the
I
answer?
don't know.
2?
So here we have binomials. Just like we've done every other time you can multiply out binomials, you just FOIL it. Okay? You FOIL it out. Okay? Distributive property and go. Billy binomial makes his appearance. 4 times 5. 4 and 4 root 2. 2 and a 2 root 2 and a 5. And then the last one is usually where people get a little messy. This becomes 2 root 2 times 4 root 2. When you have numbers and radicals put together, Yes. Put together. So always take care of your numbers first. So we have 2 times 4, which is 8. So I have 8 times root 4, otherwise known as 2. So it's 8 times 2 is 16. So we have 20 plus 26 root 2 plus 16. Now, when I put this in my final official order, you always put your integer value stuff first, and then things with radicals last. It's kind of like how we did with the I values. Remember we put the integer value first, and then we do I's later on? Yeah, so it becomes 36 plus 26 root 2. And that would be my answer.
Let's say there was an I in this equation too, so would that be like after all this stuff?
The I value, if it was like a 26 I root 2, or it was like a plus I thrown in there.
Yeah, like the end, like plus I.
The plus I would be at the very end. Yes, ma'am?
Wait, where'd you get 16?
I got the 16 from 2 root 2 times 4 root 2. So I get 2 times 4 is 8. Root 2 times root 2 is the square root of junk times the square root of junk, which is junk. So I get 8 times 2.
Yeah.
So again,
Oh, I got it.
what if I don't give you one of those?
Then.
See, I like this, like, even if I feel like I understand what I'm doing, like now I'm gonna get instant feedback about like how I do it.
And it's great how it says, good job. So all you're doing, whenever you're multiplying stuff radically, take care of the numbers first and then values. So you.
I'm starting my
Uh-oh. Do we like radicals in the denominator? No. So we need to rationalize. So just like we did when we rationalized denominators when we had imaginary values, we had something like 2 over 3 plus I. We had to get rid of the I value. And what we did to do that is we multiplied by its conjugate. Conjugates create differences of squares. So the conjugate of 3 plus I was 3 minus I. So same idea here, I'm going to create a difference of squares. I'm going to use the same two exact values, but just change the sign in the middle. So the opposite of root 5 minus root 2 is root 5 plus root 2. And I do that to the top and bottom. Because what is this whole mess equal to? 1. All I'm doing is multiplying by some factor of 1. Excuse me. So when I do this, I'm foiling things out. But you're creating a difference of squares. Remember the rules for difference of squares. If it's a squared minus b squared, that equaled a plus b, a minus b. Here's a minus b, a plus b. So my answer here, the denominator is just going to be root 5. I'm going to write out long way real quick. Root 5 squared minus root 2 squared, which is 5 minus 2. Numerator, I get 3 root 2 times root 5 plus 3 root 2 times root 2. Because I'm distributing to both parts. You okay with that?
Yes.
So root 2 times root 5 is how much? Root 10. Very good. So I get 3 root 10. 3 times root 2 is 6. Now, my numerator then, I need to rewrite it so the number comes first. And I get 6 plus 3 root 10. And just like when you had, when you multiplied out by conjugates with imaginary numbers, every so often you were able to simplify everything out. If all 3 of the coefficients had the same value, you can factor it out. All 3 of those numbers, the 6, the 3, and the 3, all have what in common? 3. I could factor out a 3 out of everything, and I'm left with 2 plus root 10. And that's it. This happens from time to time that you can simplify everything out. So what you do is you take a GCF, oops, and that simplifies, because you can simplify over division. Can't simplify over addition, but I can simplify it over division. Yeah, answer 2 plus root 10. That's how these work. You're multiplying by conjugates. Quite honestly, the only thing that you might mess up if you're multiplying by conjugates is when it might look like this. If you've got like a 2 root 3 plus 4, when you FOIL it out, you might forget that there's a 2 out here. So you might accidentally just say it's 6 instead of 4 times 3, it's 12. So just be careful if you have a coefficient in front of your radical, make sure you multiply that out. That's all. That's really the only mistake that I normally see with people when they do this. When you FOIL this out, a lot of times people just do 2 times 3. They forget it's 2 times 2 times 3. That's what I'm getting. They forget that it's there. Okay. Yes, sir.
What happened if we just multiply by root 3 minus 4? Then
It wouldn't be,
because
you would eliminate the radical.
Then we put 3 minus 4, then root 3 minus 4.
I really tried. But then it's not a true difference of squares. See what I'm saying? It does. Because if you do a true difference of squares, you FOIL everything out. Doing it that way, you'll still have middle term. If you do just this,
Okay.
if you do that, you'd still wind up with the middle term that doesn't cancel out. By doing it this way, it allows you to cancel out the middle term. Does that make sense? I thought you were talking about because here, there's a GCF, I could have done something weird. What's that?
Can you go back to like the last page?
Yeah.
I don't like,
Where are you at?
no, yeah, like the 3 and then the root 2 and then times root 2. Like, how do you get a
This was just, this here, all I did was 3 root 2
Yeah.
times root 5 plus root 2. And I just distribute it in.
No, not that one. I was the other one. I'm confused with the easy part.
Which one, here?
Yeah.
All right, what's root 2 times root 5?
Oh no, not that one. The second half. Of it.
Okay,
Yeah.
this is 3 times the square root of 2 times the square root of 2.
Yeah.
What's the square root of 2 times the square root of 2?
Square root of 4.
What's the square root of 4? What's 2 times 3?
Oh, you multiplied that. Okay. So I was confused. Okay. I didn't understand like how you got like 3 and
And that's how that stuff works. Now, the other part that I wanted to show you guys was if I do this also in, separate. The only other weird part or weird thing I want to show you is something we've actually talked a little bit about. And this kind of stems into the 6-4 stuff. Is how you work with the exponents. We've discussed this. I did show you. Any nth root can be rewritten as a fractional exponent. Remember when we talked about square roots were what exponent? Half. Square roots was x to the 1/2. Cube roots were x to the fourth roots are x to the fourth.
Yeah.
So basically what we're talking about here is any nth root can be rewritten as a fractional exponent. So what you get here is the nth root of x is x to the 1/n. And it works going both ways. You okay? You look half asleep just staring ahead?
Please don't change the slide.
That is how I roll. That would be something I would do. Okay. Now, same thing goes for if I had, what happens if I have x to the m over n? Where, let's say this was x, well, I'll do this first. My nth root is always going to be the denominator of my fractional exponent. The nth part then would be what power it's raised to underneath the radical. For example, if I write x to the m over n, that would be the nth root of x to the m. So when you had stuff, I think we had this yesterday. Didn't we have like the cube root of x squared? And we couldn't simplify that? If I wanted to write that as a fractional exponent, that would just be x to the 2/3. What's that?
So you could solve for it.
You could, but the reason why I would do a fractional exponent is if I'm raising it to another exponent, because remember the powers of exponents? Power to power, or you multiply things through, you can simplify the fractional exponents easier with you can simplify nth root exponents easier as fractions than you can as nth roots. Because all you're doing is adding or subtracting fractions. Okay. So what this allows me to be able to do is something like this. Which one was it? I can say that the 2/16, this didn't show up at all. 2/16 to the 1/3 is what as an nth root? It's the cube root of
216.
take a guess. What do you think the cube root of 216 is? 6.
6.
All right, what about this? 7 to the half times 7 to the half. Are those same bases? What do you do to the exponents when you multiply them? You add them. What's 1/2 plus 1/2? Which is 7. Isn't this the square root of 7 times the square root of 7? Which is 7. Yes, ma'am.
Would it be okay if you always like thought back to the rational?
It's fine if you want to. And I was just saying, Sarah, that a lot of times when you're simplifying with a lot of exponents, it is so much easier to work with them in terms of fractions than it is nth roots. If you're given stuff as an nth root to start with, use the trick of simplifying out with division. If you're given to you in fractional form, add and subtract. Okay. Like this.
Oh, not the B one.
If I do this, the way it stands, the square root of x cubed over the cube root of x squared. Quite the conundrum. If I convert those both to a fractional exponent, you can play the game of war rather quickly. The nth root here is what? 2. So this is x to the 3/2 over x to the 2/3. What's bigger, 3/2 or 2/3? 3/2. So all you have to do then is figure out what's going to be 3/2 minus 2/3, which is a very simple common denominator to get. What's going to be the common denominator? 6. 6. So multiply the bottom one here by 3, multiply the top one by 3. I get 9/6 minus, was it 4/6? So then I get, for my answer, x to the 5/6. That's the reason why we worry about and work with nth roots conversion to fractions, because you can manipulate and simplify things easier. Because you have the same base, but yet you might not have the same exponent. Yes, sir?
Do you as the 6th
Yeah. Yeah. And then depending upon what instructions say, sometimes it might say leave your answer in the fraction form, or not in nth root, or it might say in fractional form. I think more often than not, I don't. It really depends on what it asks. I think the old book does it both ways. I don't remember if this book does one or the other. Yes, ma'am. Yeah, this would be one way to write the answer, or the other one would be the 6th root of x to the 5th. Both of those are equivalent statements because of the rules of nth roots and exponents. Okay. Lynn?
That's like the common movie thing.
I'll stop. Let you guys figure out the rest. We'll continue tomorrow. There's 2 of them set up for you already in the Excel thing. Just kind of crawl through them.
Wait, do I have
Yeah.
wait, do you want us to do this one?
No, you can work on it. I think that problem even comes up in the Excel. So I wanted to give you guys time to start on it. Yes, ma'am. Yeah, what do you got?
Did you just multiply the fractions by 3?
I multiplied. I almost used a pen on the board.
That would have really bad.
I multiplied this one by 3 over 3, and this one by 2 over 2. I just got the common denominator.
She married her dad?
You forgot common denominator.
Oh, okay.
Pretty soon we'll even get to the point of having to add, subtract common denominators with polynomials. That's exciting. Very exciting. LeBlanc, you look worried. What's wrong? The triangle problem? What's if your sides are if your sides are 16 on a if your sides are 12 of a rectangle, or I'm sorry, of a square, what's your hypotenuse?
Chocolate cake is so good.
No.
Yes.
Are you dealing with the squares? Okay. If you're dealing with the squares,
Wait, what is 7 plus 5?
what's your diagonal?
Good job.
Diagonal, excuse me. What's your diagonal?
What? Wouldn't that just be 8?
That's all it is. 12 root 2 then. Yes, did you see my part of me to die? One of the most important things you learned last year.
Oh, that? I feel like every time I mess up that I'm disappointed in like something.
Just so you guys know, those two triangles, you are going to absolutely love them. And the importance of knowing how to work with the sides opposites and adjacents built out of those two, because those two triangles are the entire basis of all trigonometry. Everything we do second semester with unit circle and everything else is graphic. What's that? The unit circle, yes.
Stop.
1, 1, or 2. Oh yeah. Everything that you need to know is those two triangles.
I think you take the time to
No, the circle itself that I'm talking about is where it builds out.
That is not the right
That.
answer.
Because every one of these points is reflected and flipped. And it just works with order. All you're doing is working with ordered pairs, and it shows the oscillation for creating sine and cosine waves and tangent. It's all built out of that. Hold on, let me stop this real quick. Excuse me.
Oh, your birthday's in 2 weeks.